Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into a question that sounds simple at first, almost innocent, yet quietly shapes everything that exists. Why the speed of light is not just about light at all, but about how reality itself is allowed to unfold. Before you settle in, if you find these gentle explorations comforting, you're always welcome to leave a like or subscribe, only if it feels right. And when you're ready, you might share where in the world you're listening from and what time it is for you right now. It's always a quiet joy to imagine so many minds drifting together, each in their own corner of the night. Now, dim the lights if you can. Let your shoulders soften. Perhaps take one slow breath. We're about to wander through human curiosity, failed experiments, strange limits, and a universe that seems to whisper, "Not faster than this." And if your attention drifts, that's perfectly fine. The story will keep unfolding patiently, whether you're awake or already beginning to rest. From the very beginning, humans have been creatures who measure. We measure the length of our days by the rising and setting of the sun. We measure distance by how long it takes our feet to grow tired. We measure danger by how quickly we must run away from it. Speed, in this sense, is deeply human. It tells us whether we can catch something, escape something, or understand something before it's gone. Long before equations and laboratories, speed was survival. Light, however, always felt different. You can hear thunder roll across the sky, counting the seconds until it arrives. You can watch a bird take flight and trace its path through the air. But light seems to appear all at once. When a torch is lit, darkness simply retreats. There is no sense of motion, no waiting, no gradual arrival. For most of human history, light felt instant, almost magical. It didn't behave like anything else we knew. This sense of immediacy shaped early intuition. If something feels instantaneous, the natural conclusion is that it has no speed at all, or perhaps that its speed is infinite. For centuries, this idea felt reasonable. Light didn't announce itself as something that travelled, it simply was. Philosophers debated it, but everyday experience offered no contradiction. There was no obvious delay to measure, no gap to observe. Light seemed to belong to a different category altogether, and yet curiosity has a way of refusing comfort. As tools improved and questions sharpened, people began to wonder whether instant was truly instant, or merely too fast for human senses to notice. This was not idle curiosity. To understand light was to understand vision, astronomy, and eventually the structure of the heavens themselves. Measuring the speed of light became more than a technical challenge. It became a test of whether human intuition could be trusted. What makes this question so gentle, yet so profound, is that it begins with something almost childlike. How fast does light move? It sounds like the kind of question someone might ask while watching a candle flicker or the sun dip below the horizon. And yet hidden inside it is a deeper one. Does the universe allow anything to be truly instantaneous? Or does everything, no matter how subtle, take time? At first, the motivation to measure light had little to do with cosmic limits or the nature of reality. It was practical, even humble. Astronomers wanted to know how far away the stars were. Navigators wanted better maps of the sky. Timekeepers wanted more precise clocks. Light, it turned out, sat quietly at the centre of all of these ambitions. To measure distance across the heavens, one needed to understand how light carried information from faraway places. There is something quietly poetic about this. Long before we suspected that light speed might be a fundamental limit, we were already relying on it as a messenger. Every star we see is telling us a story that began long ago. Every sunrise is an ancient signal finally arriving. Even before we knew it had a speed, light was already teaching us patience. As people began to take the idea seriously that light might move at a finite pace, the challenge became clear. How do you measure something faster than any horse, any arrow, any sound? You cannot chase it. You cannot race it. You cannot easily place two clocks far apart and ask them to agree. The universe does not make this easy, and perhaps that is part of the lesson it was quietly offering. The earliest attempts to measure light speed were not grand or elaborate. They were simple, almost naive, and deeply human. They reflected a belief that if we just tried hard enough, we could catch light in the act of moving. These attempts would fail not because the people involved lacked intelligence, but because light was already hinting that it did not fit into the ordinary rules of motion. What's important here is not the failure itself, but what failure revealed. When a question refuses to yield to straightforward methods, it often means the question is pointing towards something deeper than expected. Light was not merely fast, it was different. And the sooner humans realized this, the sooner they were forced to confront a more unsettling possibility. That speed itself might have a special role in the universe, one that could not be adjusted, negotiated, or bypassed. In this way, the simple urge to measure became the first step toward a much larger realization. Humans were not just trying to measure light. They were unknowingly probing the rules that govern cause and effect. They were testing whether the universe had a maximum pace at which it could respond to itself. They just didn't have the language for it yet. As we linger here, at the beginning of this story, it's worth noticing how calm and unassuming it is. No equations are required. No advanced theories are needed. Just a question, a flicker of curiosity, and a sense that something important is hiding behind what feels obvious. Light appears instantly, so we assume it must be infinite. But the universe, as it often does, is about to gently disagree. And so, with this quiet tension in place, the story naturally drifts toward its first real experiment. A moment when someone finally tried to catch light using nothing more than distance, patience, and the night sky. That attempt would not only reveal that light has a speed, but that it leaves subtle fingerprints wherever time and distance meet. When curiosity finally turns into action, it often begins in the simplest possible way. In the early 17th century, long before lasers and atomic clocks, the idea of measuring light felt almost approachable. If light truly had a speed, then perhaps it could be timed just like anything else. All one needed, it seemed, was distance, visibility, and a pair of willing observers. This was the spirit in which Galileo Galilei approached the problem. Galileo did not imagine light as a cosmic constant or a boundary of reality. To him it was a physical phenomenon, much like sound or falling stones. And so his approach was practical, almost playful. He proposed an experiment using lanterns. 2 observers would stand on distant hilltops at night, each holding a covered lantern. One observer would uncover their lantern, allowing the light to shine toward the other. The second observer, upon seeing the flash, would immediately uncover their own lantern in response. By measuring the delay between sending the light and receiving the return signal, Galileo hoped to measure how long light took to travel. It was a beautifully human idea. No elaborate instruments, no equations written on parchment, just hills, lanterns, and careful attention. If light took time to travel, even a tiny delay might reveal itself. And if no delay appeared, perhaps that too would be informative. Either way, the universe would be asked a question. But the universe remained quiet. No matter how far apart the observers stood, no matter how carefully they watched, the response appeared instantaneous. The light seemed to return the moment it was sent. Galileo could not detect any delay beyond the limits of human reaction time. His conclusion was cautious and honest. If light had a speed, he reasoned, it was either infinite or simply far too fast to measure by this method. What's important is not that Galileo failed, but why he failed. His experiment was limited not by intelligence or effort, but by biology. Human perception, reflexes and coordination simply could not resolve the tiny interval light required to cross even several kilometers. The delay existed, but it was buried beneath the noise of human response. Light had slipped through the cracks of our senses. This moment marks something subtle and profound. For the first time, humans were forced to confront the possibility that nature could operate on timescales beyond direct experience. Sound announces itself with delay. Motion reveals itself gradually. Light, however, seemed to mock these expectations. It behaved as though it were immediate even when it was not. Galileo's lantern showed us something unexpected. They revealed not the speed of light, but the limits of human measurement, and in doing so they hinted that light belonged to a category of phenomena that required new ways of thinking. Measuring light would not be like measuring footsteps or falling objects. It would require patience, distance on a cosmic scale, and perhaps a willingness to let the universe do the timing for us. There is something quietly comforting in this failure. It reminds us that science does not advance only through success. Sometimes, not seeing what you expect is the most valuable result of all. Galileo did not prove light was instantaneous. He proved that it was fast enough to escape the tools of his time. That realization alone shifted the question. Light was no longer simply fast, it was mysteriously fast. This is where intuition begins to loosen its grip. If light cannot be measured with lanterns across hills, then perhaps hills are not enough. Perhaps the distances involved must be vast, even astronomical. The thought naturally drifts upward, away from Earth, toward the sky. After all, the heavens had always offered humanity its longest distances and slowest rhythms. Planets wander, moons return again and again, stars rise and set with patient regularity. If light took time to travel, perhaps the sky itself was keeping the record. What Galileo could not yet know was that the solution would not come from faster reactions or sharper eyes, but from celestial clocks. Light would reveal its speed not by racing across short distances, but by arriving late from faraway places. The universe would become the experiment, and time itself would be the measuring device. And yet, even as we look back with modern understanding, Galileo's approach remains deeply instructive. It shows us how natural it is to assume that the universe will cooperate with our everyday instincts. We expect causes and effects to announce themselves clearly. We expect delays to be obvious. But light refuses this simplicity. It demands either enormous distances or extraordinary precision, both of which lie far beyond casual observation. There is also something poetic in the image of two lanterns flashing across the dark. It captures a moment when humanity reached out, not knowing whether anything would answer. The answer came in silence, not because light had nothing to say, but because it was already telling a story too subtle to hear. This silence did not close the question, it sharpened it. If light was not infinite and not measurable by human reaction, then it occupied a strange middle ground, finite yet effectively unreachable, present everywhere yet impossible to catch in motion. The universe was beginning to hint that light was not just another traveller moving through space, but something more fundamental, something woven into the structure of space itself. As the night deepens in our story, the focus gently lifts from hilltops to orbits, from lanterns to planets. The problem remains the same, but the scale changes. To measure light, we must stop trying to outrun it and instead learn how to wait for it. and somewhere among the steady movements of the solar system, that opportunity quietly appears. After Galileo's lanterns faded into silence, the question of light's speed lingered without urgency. It was not abandoned, but it rested, waiting for the right conditions to speak again. Those conditions did not appear on Earth. They appeared far away, among the slow and predictable motions of the solar system. The solution, it turned out, was not to chase light, but to notice when it arrived late. In the late 17th century, the Danish astronomer Ole Rømer was studying the motion of Jupiter's moon Io. Io is a remarkably punctual object. It orbits Jupiter with steady regularity, disappearing behind the planet and re-emerging again and again like a reliable cosmic heartbeat. To astronomers, these eclipses were not merely interesting, they were useful. Each disappearance and reappearance could be predicted with precision, offering a kind of natural clock written into the sky. At first, everything seemed orderly. Io's eclipses followed their schedule, and predictions matched observations. But over time, something subtle began to emerge. The eclipses did not always occur exactly when expected. Sometimes they appeared slightly early, sometimes they arrived slightly late. The pattern was not random. It followed Earth's position in its own orbit around the Sun. When Earth was moving closer to Jupiter, the eclipses appeared sooner than predicted. When Earth was moving farther away, the eclipses arrived late. The delay grew as the distance increased and shrank as the distance decreased. This was not a flaw in the clock. It was the clock revealing something else. Rømer realized that the simplest explanation was also the most unsettling. Light was not reaching Earth instantly. It was taking time to travel across space. When Earth was farther away from Jupiter, the light from Io had farther to go and it arrived later. When Earth was closer, the journey was shorter and the signal arrived sooner. Distance, it seemed, was stretching time. This was a quiet revolution. There were no flashes, no sudden revelations, no dramatic apparatus, just careful observation and patience. Light had finally been caught, not by speed, but by delay. The universe had been keeping time all along, and someone had finally noticed. What makes Rømer's insight so powerful is how gentle it is. Did not need to know the exact distance between Earth and Jupiter in modern units. He did not need advanced instruments. He needed only to recognize a pattern and trust it. The difference between early and late eclipses amounted to minutes, not seconds, but over astronomical distances, those minutes mattered. For the first time, light was revealed as something that travelled, something that moved through space rather than appearing everywhere at once. Its speed was enormous, far beyond anything humans could sense directly, but it was not infinite. This distinction, subtle as it may seem, changed everything. The idea that light had a finite speed reshaped how humans understood the sky. The stars were no longer just distant points of brightness. They were messengers from the past. To look at Jupiter was to see it not as it was now, but as it had been moments ago. To look at distant stars was to peer further back in time. Space and time, once treated as separate ideas, began to blur together. There is something almost soothing about this realization. It tells us that the universe is not rushing. Information does not leap instantly from place to place. It travels patiently, carrying history with it. Every signal takes time. Every observation is a glimpse into what once was. The night sky becomes a library of delayed messages, each arriving on its own schedule. Rømer's work did not immediately convince everyone. The idea that light had a speed was still unsettling, and its implications were not yet fully understood. But the door had been opened. Once light was known to be finite, the question could no longer be ignored. How fast did it travel? And more importantly, why did it have a speed at all? The measurement itself, while groundbreaking, was still rough by modern standards. It did not give a precise value in familiar units, but precision was not the point. The point was existence. Light took time, distance mattered, the universe respected delay. This realization gently nudged physics away from intuition and towards structure. If light required time to travel, then space was not just an empty stage. It was something light interacted with, something that shaped how information moved. The universe was beginning to look less like a static backdrop and more like an active participant. There is also a deeper lesson hidden here, one that fits quietly into the rhythm of this story. Römer did not speed anything up to catch light. He slowed himself down. He watched cycles repeat. He waited for discrepancies to accumulate. This is often how nature reveals its secrets, not through force, but through patience. As we rest in this moment, it becomes clear that measuring the speed of light was never just about numbers. It was about discovering that the universe has a tempo, a maximum pace at which changes can propagate, a rhythm that even light must follow. With Römer's insight, the question shifts again. Light has a speed. It is finite. It can be measured. But what determines that speed? Is it a property of light itself, or is it something deeper, something woven into space and time? The answer to that question would not come from astronomy alone. It would require a collapse of old ideas and the birth of a new way of thinking. And so, as Earth continues its slow orbit and Jupiter keeps its steady watch, the stage is set for a much larger transformation. Light has been timed, now it must be understood. Once light was known to have a finite speed, a new question naturally took its place. If light travels, then what does it travel through? For sound, the answer is obvious. Sound needs air, water, or some material to carry vibrations from one place to another. For waves on the ocean, water itself rises and falls. For ripples on a pond, the surface of the water does the moving. In everyday life, waves always seem to belong to something. It felt only reasonable that light should be the same. This reasoning gave rise to one of the most enduring ideas in the history of physics, the ether. The ether was imagined as an invisible, weightless substance filling all of space. It was not matter in the usual sense, but it was not nothing either. It had just enough presence to carry light waves, and just enough subtlety to avoid interfering with planets, stars, or everyday motion. In many ways, it was the perfect solution. It explained how light could behave like a wave while travelling through what otherwise appeared to be empty space. More importantly, the ether was comforting. It allowed physicists to keep their familiar intuitions intact. Space could remain a passive container. Motion could remain absolute. Light could remain a wave moving through a universal background. Nothing fundamental needed to change. The universe still made sense in the way people were used to. For decades, the ether was not a fringe idea. It was central. Textbooks assumed it. Experiments were interpreted through it. Calculations quietly depended on it. To question the ether was to question the very language physicists used to describe reality, and most had no reason to doubt it. After all, the ether did not need to be seen. Its job was simply to be there, everywhere, all the time. But there was a problem hiding beneath this neat picture. If the ether filled all of space, and if Earth moved through space as it orbited the Sun, then Earth should be moving through the ether as well. That motion should have consequences. Light travelling in the direction of Earth's motion should behave differently from light travelling across it, much like how walking into the wind feels different from walking sideways through it. This idea led to a simple but profound expectation. There should be an ether wind, a subtle difference in how light travels depending on the direction of Earth's motion. Detecting this wind would not only confirm the ether's existence, but also allow scientists to measure Earth's speed through this invisible medium. It seemed like a matter of careful experimentation. The stage was set for a decisive test. What makes this moment in the story especially gentle and slightly ironic is that the experiment designed to detect the ether was exquisitely precise. It was not rushed. It was not careless. It was carried out with extraordinary attention to detail. The universe was being asked a clear question, and every effort was made to listen closely to the answer. And yet, when the experiment was performed, the universe responded with silence. No matter how the apparatus was rotated, no matter the time of year, no matter the direction of Earth's motion, light behaved the same. There was no detectable ether wind. Light did not seem to care about Earth's movement through space. It arrived with the same speed in every direction. At first, this result was unsettling, but not immediately revolutionary. Many assumed the experiment must be flawed or that the ether behaved in a more complicated way than expected. Perhaps it clung to Earth. Perhaps it was dragged along by matter. Perhaps its properties changed subtly depending on circumstances. New explanations were proposed, each one designed to protect the ether from abandonment. This reaction is deeply human. When an idea has served us well for a long time, we instinctively try to save it. We add layers, we adjust assumptions, we search for loopholes. The ether was not just a scientific concept, it was a psychological anchor. Letting it go meant admitting that space itself might not behave the way we imagined. What makes the ether story so important is not that it was wrong, but that it was reasonable. It emerged naturally from analogy and experience. It reflected how humans had learned to understand waves and motion. The failure of the ether was not a failure of logic. It was a failure of intuition when pushed beyond its domain. As the evidence against the ether accumulated, physics entered a quiet crisis. The equations still worked. Predictions were still accurate. But the underlying picture no longer held together. Light behaved as if there were no preferred background, no universal stage, no invisible substance defining rest and motion. Space itself seemed oddly indifferent. This kind of crisis is different from dramatic collapse. Nothing explodes, nothing visibly breaks. Instead, confidence erodes. The old explanations begin to feel heavy, patched together, strained. Something simpler seems to be waiting, but it has not yet been named. In hindsight, the ether failed because it asked the wrong question. It assumed that light needed a medium because everything else we knew did. But light was never just another wave. It was a signal, a messenger, a carrier of information. It did not require a substance to wiggle. It required a structure in which cause and effect could propagate. This realization, however, would take time. For now, physicists stood in an uncomfortable space between belief and doubt. The ether could not be detected, yet removing it felt like pulling away the floor beneath their understanding. What would space be without it? How could motion be defined without a background? How could light travel through nothing? These questions lingered, unresolved, creating a tension that could not be ignored forever. The universe had spoken clearly. There was no ether wind. No hidden medium revealed itself. Space was quieter, emptier, and stranger than expected. And in that quiet, a deeper possibility began to form. Perhaps space itself was not an empty container at all. Perhaps it had structure, rules, and relationships that did not require a material substance. Perhaps the speed of light was not determined by what it moved through, but by how reality itself was arranged. This is where the story naturally pauses, not with an answer, but with a readiness. The ether has faded, the old intuitions are loosening, a new idea is waiting to be spoken, one that will not try to save the familiar picture but replace it entirely. And when it arrives, it will begin not with light, but with time. The idea of the ether had survived for so long because it felt inevitable. Waves needed something to wave in. Space surely could not be truly empty. But belief alone is never enough in science. If the ether existed, it had to leave traces. And by the late 19th century, physicists had developed instruments delicate enough to go looking for them. Albert Michelson and Edward Morley set out to do exactly that. Their goal was not to overturn physics, but to confirm it. The ether was assumed to be real. What remained was to measure Earth's motion through it. This motion should have created a subtle difference in how light behaved depending on direction, much like how a swimmer feels a current more strongly when moving upstream than across it. To test this, they built an instrument of extraordinary precision. A beam of light was split into two paths at right angles. One beam travelled in the direction Earth was expected to be moving through the ether. The other travelled sideways. After reflecting off mirrors, the two beams were brought back together. If one beam had taken slightly longer than the other, the difference would reveal itself as a shifting pattern of light and dark, a delicate interference signal acting as a cosmic stopwatch. The expectation was clear. As Earth orbited the Sun and rotated through space, the speed of light along one path should change relative to the other. The pattern should shift. The ether wind should announce itself. It never did. No matter how carefully the apparatus was rotated, no matter the time of day or season of the year, the result remained the same. The light beams returned together. There was no measurable difference. The expected signal simply was not there. At first, this was deeply unsettling. The experiment was sound. The instruments were precise. The reasoning was straightforward. And yet the universe offered no confirmation. The silence was not subtle. It was complete. This is one of the most important moments in the history of science, not because something dramatic happened, but because nothing did. The experiment did not explode, fail mechanically, or produce ambiguous data. It worked exactly as designed. And that was the problem. Faced with this result, physicists did what humans often do when a trusted idea is threatened. They tried to save it. Perhaps the ether was dragged along with Earth. Perhaps objects physically contracted in the direction of motion in just the right way to hide the effect. Perhaps time itself adjusted slightly, compensating for the difference. These ideas were clever, mathematically consistent, and increasingly complicated. Each adjustment preserved the ether, but at a cost. The picture of reality was becoming patched and fragile, held together by assumptions that existed only to protect something no one could detect. The simplicity that once made the ether appealing was slipping away. What makes the Michelson-Morley experiment so powerful is that it forced a choice. Either the ether existed in a form that could never be measured and required constant explanation, or the underlying assumptions about space and motion were wrong. The experiment did not tell physicists what to believe. It told them what they could no longer comfortably believe. Slowly, reluctantly, the idea took hold that perhaps light didn't need a medium at all. Perhaps there was no universal background defining rest and motion. Perhaps the universe didn't care how fast you were moving through space when it came to light. This was not a conclusion anyone rushed toward. It was one they backed into, guided by evidence that refused to cooperate with intuition. There is something quietly humbling in this. Humans built an experiment expecting nature to confirm their picture. Nature responded by doing nothing extraordinary. And in that nothing, it revealed something profound. Space did not behave like a substance. Motion was not absolute. Light was not riding on an invisible sea. This moment marks the end of a certain kind of thinking. Up to this point, physics had relied on the idea that there was a preferred frame of reference, a cosmic stillness against which all motion could be measured. The ether was meant to provide that stillness. Without it, the concept of absolute motion began to dissolve. The implications were unsettling but also liberating. If there was no universal background, then motion itself might be relative. If light behaved the same for all observers, regardless of how they moved, then perhaps the rules of space and time were not fixed in the way people had assumed. The universe was inviting a simpler explanation, one that did not require invisible substances or special exceptions. Importantly, the Michelson-Morley experiment did not immediately explain why light behaved this way. It only made one thing clear: the old explanations were no longer sufficient. The ether was not just unnecessary, it was obstructive. It stood in the way of understanding something deeper. In the calm aftermath of this realization, physics found itself suspended between certainty and discovery. The measurements were precise, the conclusions were unavoidable, but the new picture had not yet been drawn. Space was behaving as if it had no preferred state of rest. Light was behaving as if its speed did not depend on motion through anything. Time itself seemed poised to enter the conversation. This is where the story gently turns. The silence of the ether did not answer the question of light's speed. It reframed it. Instead of asking what light moved through, physicists were now forced to ask why its speed remained the same, no matter who measured it. That question would soon find an answer, not in the properties of light, but in the structure of reality itself. And so, in the stillness left behind by a missing ether wind, a new idea began to take shape, one that would not try to rescue the old picture, but would quietly replace it with something simpler, stranger, and far more powerful. After the Michelson-Morley experiment, physics did not collapse in a dramatic flash. There were no headlines declaring the end of classical thought. No equations were torn up overnight. Instead, something far more unsettling happened. Everything still worked, and yet nothing felt secure. The equations of electromagnetism continued to predict experiments correctly. Engineers could still build devices, astronomers could still calculate orbits. Light still reflected, refracted, and interfered exactly as the mathematics said it should. From a practical point of view, physics was functioning beautifully. And yet, beneath this surface of success, the meaning of those equations was slipping away. This is a strange kind of crisis, one that is easy to miss when looking back. We often imagine scientific revolutions as moments when old theories fail outright. But here, the opposite was happening. The theories worked too well. They delivered correct answers while refusing to explain why those answers made sense. The ether had provided an intuitive backdrop. It had given physicists a way to picture what was happening. Light was a wave. Waves need a medium. Space was the stage. The ether was the substance on that stage, and motion could be measured relative to it. With the ether gone, the stage remained, but the substance vanished. The actors were still performing, but no one could say what they were standing on. This left physicists in an uncomfortable position. They could calculate, but they could not visualize. They could predict, but they could not explain. The familiar language of absolute space and absolute time no longer fit the evidence, yet nothing obvious was ready to replace it. Attempts were made to patch the situation. Some proposed that objects physically shorten themselves in the direction of the motion, just enough to hide the ether wind. Others suggested that clocks slowed down in a compensating way. These ideas were mathematically clever, and importantly, they worked. But they felt artificial. They existed to protect an assumption rather than to illuminate reality. What was missing was not a new equation, but a new perspective. At the heart of the problem was a quiet contradiction. Electromagnetism, the theory that described light, insisted on a single, fixed speed for light. Classical mechanics, the theory that described motion, allowed speeds to simply add together. If you throw a ball from a moving train, its speed depends on how fast the train is going. Light, according to experiments, refused to behave this way. No matter how the source moved, light arrived at the same speed. This refusal was not loud or dramatic. It was persistent. It showed up in every careful measurement and every precise experiment. The universe was calmly insisting on a rule that did not fit the existing framework. The deeper physicists looked, the clearer it became that the problem was not with light. It was with time. Classical physics treated time as universal, flowing at the same rate for everyone, everywhere. Clocks were assumed to agree by default. Events were assumed to have a single, absolute order. These assumptions had never been questioned because they had never needed to be. Now, quietly, they were being questioned by light. If light speed was truly the same for all observers, then something else had to give. Either distances were changing, or time was behaving differently, or both. The idea that time itself might depend on motion was unsettling. Time felt too fundamental, too familiar, too deeply woven into experience to be flexible. And yet, the evidence left little room for alternatives. This is where the crisis becomes almost philosophical. Physics was confronting the limits of intuition. The concepts that had once seemed self-evident were revealing themselves as approximations, useful only within a narrow range of experience. The universe was not obligated to match human expectation. It was only obligated to be consistent. There is something quietly profound about this moment. It is the realization that understanding requires surrender. Not surrender in the sense of giving up, but in the sense of letting go of assumptions that no longer serve. The ether had been one such assumption. Absolute time was about to be another. Importantly, this period was not one of despair. It was one of tension, a sense that a simpler, deeper explanation was close, but not yet visible. Physicists could feel that the pieces were almost fitting together. Light, space, and time were clearly connected, but the nature of that connection had not yet been named. This tension created a kind of intellectual stillness. The old ideas were no longer trusted, the new ideas had not yet arrived. In this quiet gap, physics waited. Looking back, this pause feels inevitable. Revolutionary ideas rarely emerge in noise. They emerge in silence, when contradictions are allowed to sit unresolved. The failure of the ether did not demand immediate answers, it demanded patience. In that patience, a new way of thinking began to form, one that would stop asking what light moves through and start asking how space and time themselves might adjust to preserve consistency. One that would treat the speed of light not as a property of a particular phenomenon, but as a clue to the structure of reality. This shift did not come from more complicated machinery or more precise measurements. It came from re-examining assumptions so basic that no one had thought to question them. What if time was not universal? What if space and time were not separate? What if the speed of light was not something to be explained, but something to be respected? These questions hovered quietly, unanswered, like the pause before a breath. And in that pause, the stage was set for a young patent clerk to propose something radical, elegant, and almost disarmingly simple. The universe had spoken clearly. Light behaved the same for everyone. Space offered no preferred frame. Time, it seemed, was no longer safe from scrutiny. The crisis had no explosion, but it had momentum, and it was about to carry physics into a new understanding of reality itself. In the long pause left behind by the ether's disappearance, physics needed a new starting point. Not a patch, not a clever adjustment, but a principle simple enough to replace everything that had quietly failed. That principle did not arrive with thunder or complexity. It arrived almost shyly, as a question asked in the right way. What if the universe was telling us something directly? Every experiment suggested the same strange fact. No matter how the source moved, no matter how the observer moved, light, always arrived at the same speed. This was not an approximation. It was not an accident. It was consistent, stubborn, and universal. Instead of asking how to explain this away, a young physicist named Albert Einstein asked a different question. What if this is simply how the universe works? This shift in attitude was everything. Rather than treating the constant speed of light as a problem to be solved, Einstein treated it as a clue. He proposed that the laws of physics, including the behavior of light, should look the same to all observers who are moving steadily, without acceleration. No special frame, no hidden background, no preferred state of rest. At first glance, this idea feels harmless, almost obvious. Of course, physics should work the same for everyone, but when combined with the observed behavior of light, it led to consequences that were anything but obvious. If light speed is the same for everyone, then something else must change to make that possible. Distances cannot be fixed. Time cannot be universal. The old assumptions quietly give way. Space and time, once treated as separate and absolute, begin to behave like flexible partners in a shared dance. To understand this, imagine two people watching the same event from different motions. One stands still, the other glides smoothly past. In everyday life, we expect them to agree on what happened and when, but light complicates this expectation. If both observers measure light travelling at the same speed, then they cannot agree on the timing of events in the same way. The universe quietly refuses to allow both expectations to coexist. Einstein's insight was to accept this refusal rather than fight it. He recognized that time itself must adapt. Clocks moving relative to one another must tick at different rates. This is not because they are faulty or broken, but because time is not a single river flowing identically everywhere. It is more like a landscape shaped by motion. This idea is unsettling because time feels personal and intimate. We experience it directly. We feel moments pass. We trust clocks. To suggest that time depends on motion feels like suggesting that experience itself is negotiable, and yet the universe insists. There is a calm elegance to this insistence. Rather than breaking physics, it simplifies it. Once we accept that time can stretch and compress, the strange behavior of light no longer needs explanation. It becomes natural. Light is not adjusting itself to observers. Observers are adjusting their measurements to remain consistent with light. In this picture, light is no longer just a traveller moving through space. It becomes a reference, a standard, a boundary that all observers share. The speed of light becomes a kind of agreement the universe enforces, ensuring that cause and effect remain coherent. It is important to notice how gentle this idea actually is. Einstein did not propose new forces or hidden mechanisms. He did not introduce exotic substances. He asked us to reconsider what we mean by time and space. The universe did the rest. When people first encountered these ideas, many resisted them. Time slowing down sounded absurd. Lengths shrinking sounded like illusion. But experiments would eventually confirm these effects again and again. Clocks carried on fast-moving vehicles really do tick differently. Particles moving near light speed really do live longer. These are not tricks. They are consequences of respecting the universe's chosen pace. What makes this moment in the story so important for our larger question is that it redefines what the speed of light represents. It is no longer simply how fast something moves, it is how fast information can travel, how quickly one event can influence another, how tightly cause and effect are bound together. By accepting light's speed as a fundamental feature of reality, Einstein transformed a frustrating mystery into a guiding principle. The universe was no longer required to explain why light behaved the way it did. Instead, everything else had to align with it. This is a profound inversion. Light stops being the thing we measure and becomes the ruler itself. Time stops being absolute and becomes responsive. Space stops being rigid and becomes adaptable. All of this flows from a single quiet acceptance that the universe has a maximum speed and that speed belongs to everyone equally. There is something deeply reassuring in this symmetry. No observer is privileged. No motion is special. The rules apply gently and universally. Whether you're standing still, drifting through space, or riding a beam of imagination across the cosmos, the structure remains the same. As we sit with this idea, it becomes clear that the speed of light is not merely a number. It is a statement about fairness, consistency, and order. It tells us that the universe values coherence over convenience, that it will reshape our intuitions rather than compromise its structure. With this new perspective in place, the crisis that once felt paralyzing begins to dissolve. Space and time are no longer rigid scaffolds, they are dynamic participants. And light, once a mystery to be measured, becomes the quiet guide that holds everything together. From here, the path forward is no longer blocked by contradiction. Instead, it opens into a deeper exploration of what happens when time stretches, space adapts, and reality organizes itself around a single shared limit. The universe has set the pace. All that remains is to listen. Once the idea settles in that light moves at the same speed for everyone, no matter how they travel, the universe begins to rearrange familiar ideas in subtle ways. Nothing shatters, nothing announces itself loudly. Instead, everyday concepts quietly loosen their edges. Time stretches, space softens, and what once felt solid reveals itself as flexible. To understand why this happens, it helps to let go of the idea that space and time are separate containers. In everyday life, we treat them as independent. Space is where things are. Time is when things happen. They feel distinct, almost unrelated, but light refuses to respect this separation. Light ties distance and duration together into a single relationship. If light's speed is fixed, then covering more distance must always require more time, and any attempt to change one must reshape the other. Imagine two people watching the same clock. One is standing still, the other is moving smoothly past at a great speed. Both agree that the clock ticks steadily, but they do not agree on how much time passes between ticks. This disagreement does not come from faulty clocks or confused observers. It comes from the universe maintaining its rule about light. To keep light's speed the same for both observers, time itself must adjust. This adjustment is what we call time stretching. Clocks in motion tick more slowly compared to clocks at rest. Not because motion damages them, and not because time is being delayed in a mechanical sense, but because time is responding to motion in order to preserve consistency. The universe is not slowing clocks as a punishment, it is balancing its own equations. What makes this idea difficult at first is that we rarely notice it. In daily life, the speeds we encounter are tiny compared to the speed of light. The effect exists, but it is far too small to feel. It is like watching a glacier move from a single afternoon. The motion is real, but patience is required. And yet, when objects move fast enough, the effect becomes undeniable. Particles created high in Earth's atmosphere live longer than expected because they are moving close to light's pace. Clocks flown around the world return slightly out of sync with those left behind. These are not theoretical curiosities. They are measured facts, gently confirming that time is not absolute. Alongside time stretching comes space softening. Objects, moving at high speeds, become shorter along the direction of motion. This shortening is not something the object experiences as damage or compression. To the object itself, nothing feels different. Its own rulers still agree, its own clock still ticks normally. The change appears only when comparing measurements between observers in different states of motion. This is an important point to linger on. The universe is not distorting objects in some violent way. It is adjusting relationships between observers. Reality remains locally calm, even as it globally reorganizes itself. Each observer carries their own version of space and time, shaped by motion, yet all versions remain consistent with the same underlying structure. These effects are often described as strange or counterintuitive, but there is a quiet logic beneath them. The universe is not trying to confuse us. It is trying to avoid contradiction. If light is to have one speed, then measurements of distance and duration cannot remain rigid. They must become flexible enough to adapt. One way to think about this is to imagine that reality is woven from threads of space and time. Light travels along these threads at a fixed pace. When motion pulls on the fabric, the threads shift slightly. Time stretches here. Space tightens there. The weave remains intact, even if its shape changes. What is especially calming about this picture is that nothing breaks. There is no point at which time snaps or space tears. The changes happen smoothly, continuously, responding to motion in a gentle, predictable way. The universe does not resist adjustment. It accommodates it. This also helps explain why reaching the speed of light itself is not possible for anything with mass. As an object moves faster, time stretches more and more, and space along its path softens further. To push all the way to light speed would require time to stretch infinitely and space to shrink completely. The universe simply does not allow that. Not as a rule imposed from outside, but as a consequence of how everything fits together. In this sense, the speed of light is not a wall you crash into. It's a horizon you approach, but never reach. The closer you get, the more the structure of space and time adjusts, gently slowing your progress in a way that preserves order. What's important for our larger story is that these effects are not special features added to physics. They are not optional complications. They are the natural outcome of taking light speed seriously. Once that speed is fixed, everything else must follow. This realization marks a shift in how we think about limits. The speed of light is not limiting motion in a crude sense. It is shaping relationships. It tells us how events can influence one another, how causes lead to effects, and how information flows through the universe. Time stretching and space softening are not side effects. They are expressions of a deeper consistency. As we rest with this idea, it becomes clear that something even more profound is taking shape. If space and time can change depending on motion, then the order of events itself may not be as absolute as we once believed. Two observers might disagree on which event happened first, yet still agree on cause and effect. This subtle distinction will soon matter deeply. For now, it is enough to notice how quietly radical this picture is. The universe did not abandon clarity, it refined it. It allowed time and space to become flexible so that light could remain honest. And in doing so, it revealed that the speed of light is not merely a number, but a guiding rhythm woven into the fabric of existence. With this understanding in place, the story naturally drifts toward a deeper question. If light defines how time and space adjust, then what does it ultimately define about cause, effect, and the order of events themselves? The answer lies not in motion alone, but in the geometry of reality. Once the idea settles in that light moves at the same speed for everyone, no matter how they travel, the universe begins to rearrange familiar ideas in subtle ways. Nothing shatters, nothing announces itself loudly. Instead, everyday concepts quietly loosen their edges. Time stretches, space softens, and what once felt solid reveals itself as flexible. To understand why this happens, it helps to let go of the idea that space and time are separate containers. In everyday life, we treat them as independent. Space is where things are. Time is when things happen. They feel distinct, almost unrelated. But light refuses to respect this separation. Light ties distance and duration together into a single relationship. If light speed is fixed, then covering more distance must always require more time, and any attempt to change one must reshape the other. Imagine two people watching the same clock. One is standing still, the other is moving smoothly past at a great speed. Both agree that the clock ticks steadily, but they don't agree on how much time passes between ticks. This disagreement does not come from faulty clocks or confused observers. It comes from the universe maintaining its rule about light. To keep light speed the same for both observers, time itself must adjust. This adjustment is what we call time stretching. Clocks in motion tick more slowly compared to clocks at rest, not because motion damages them, and not because time is being delayed in a mechanical sense, but because time is responding to motion in order to preserve consistency. The universe is not slowing clocks as a punishment, it is balancing its own equations. What makes this idea difficult at first is that we rarely notice it. In daily life, the speeds we encounter are tiny compared to the speed of light. The effect exists, but it is far too small to feel. It is like watching a glacier move from a single afternoon. The motion is real, but patience is required, and yet when objects move fast enough, the effect becomes undeniable. Particles created high in Earth's atmosphere live longer than expected because they are moving close to light's pace. Clocks flown around the world return slightly out of sync with those left behind. These are not theoretical curiosities. They are measured facts gently confirming that time is not absolute. Alongside time stretching comes space softening. Objects moving at high speeds become shorter along the direction of motion. This shortening is not something the object experiences as damage or compression. To the object itself, nothing feels different. Its own rulers still agree. Its own clock still ticks normally. The change appears only when comparing measurements between observers in different states of motion. This is an important point to linger on. The universe is not distorting objects in some violent way. It is adjusting relationships between observers. Reality remains locally calm, even as it globally reorganizes itself. Each observer carries their own version of space and time, shaped by motion, yet all versions remain consistent with the same underlying structure. These effects are often described as strange or counterintuitive, but there is a quiet logic beneath them. The universe is not trying to confuse us. It is trying to avoid contradiction. If light is to have one speed, then measurements of distance and duration cannot remain rigid. They must become flexible enough to adapt. One way to think about this is to imagine that reality is woven from threads of space and time. Light travels along these threads at a fixed pace. When motion pulls on the fabric, the threads shift slightly. Time stretches here. Space tightens there. The weave remains intact, even if its shape changes. What is especially calming about this picture is that nothing breaks. There is no point at which time snaps or space tears. The changes happen smoothly, continuously, responding to motion in a gentle, predictable way. The universe does not resist adjustment. It accommodates it. This also helps explain why reaching the speed of light itself is not possible for anything with mass. As an object moves faster, time stretches more and more, and space along its path softens further. To push all the way to light speed would require time to stretch infinitely and space to shrink completely. The universe simply does not allow that, not as a rule imposed from outside, but as a consequence of how everything fits together. In this sense, the speed of light is not a wall you crash into. It is a horizon you approach, but never reach. The closer you get, the more the structure of space and time adjusts, gently slowing your progress in a way that preserves order. What's important for our larger story is that these effects are not special features added to physics. They are not optional complications. They are the natural outcome of taking light speed seriously. Once that speed is fixed, everything else must follow. This realization marks a shift in how we think about limits. The speed of light is not limiting motion in a crude sense. It is shaping relationships. It tells us how events can influence one another, how causes lead to effects, and how information flows through the universe. Time stretching and space softening are not side effects. They are expressions of a deeper consistency. As we rest with this idea, it becomes clear that something even more profound is taking shape. If space and time can change depending on motion, then the order of events itself may not be as absolute as we once believed. Two observers might disagree on which event happened first, yet still agree on cause and effect. This subtle distinction will soon matter deeply. For now, it is enough to notice how quietly radical this picture is. The universe did not abandon clarity. It refined it. It allowed time and space to become flexible so that light could remain honest. And in doing so, it revealed that the speed of light is not merely a number, but a guiding rhythm woven into the fabric of existence. With this understanding in place, the story naturally drifts toward a deeper question. If light defines how time and space adjust, then what does it ultimately define about cause, effect, and the order of events themselves? The answer lies not in motion alone, but in the geometry of reality. Up to this point, we have been talking about motion, time, and limits. But beneath all of these ideas lies something even more fundamental. Not how fast things move, but how events are allowed to relate to one another at all. The speed of light does not merely shape motion, it shapes possibility. To see this, it helps to stop thinking in terms of objects travelling through space, and instead think in terms of events. An event is something that happens at a place and a moment. A spark flashes, a clock ticks, a message is sent. The universe is not made of continuous motion so much as it is made of countless events stitched together by influence. The central question then becomes simple, almost gentle. If one event happens here, which other events can it affect? Which ones are forever out of reach? The answer is not written in time alone. It is written in geometry. Imagine standing on a frozen lake at night. You throw a stone onto the ice. From the point where it lands, ripples spread outward in all directions. There is a clear boundary between places the ripples can reach and places they cannot, at least not yet. The farther away you are, the longer you must wait. If you're too far, the ripples will never arrive at all. Light works in a similar way, but in a space woven together with time. When an event occurs, its influence spreads outward at the speed of light. This spreading does not fill all of reality. It traces out a shape, a kind of expanding cone that separates what can be affected from what cannot. Inside that region, cause and effect are possible. Outside it, they are not. This is what physicists call the light cone, but the name matters far less than the idea. It is the universe's way of sorting events. Some are close enough in space and time to influence each other. Others are simply too far apart. Not because of distance alone, and not because of time alone, but because of the relationship between the two. What is important here is that this structure exists whether or not anyone observes it. It is not imposed by measurement. It is built into reality itself. The speed of light acts as the slope of this structure, defining how steeply influence can spread as time moves forward. Within this structure, there is a natural order. Causes come before effects. Messages arrive after they are sent. Stories unfold one page at a time. This order is not enforced by rules or laws in the everyday sense. It emerges automatically from the way space and time are connected. Now here is where things become subtle and gently surprising. Not all events can be ordered in a universal way. Some events are so separated in space that light does not have time to connect them. For these events, there is no absolute answer to which happened first. Different observers moving differently may disagree on the order, and yet no contradiction arises. This works because events that cannot influence each other do not need a shared order. The universe does not care which one you call first if neither can affect the other. Order matters only where influence is possible. Causality, it turns out, is selective. This selective ordering is one of the most calming features of modern physics. It means the universe does not demand unnecessary precision. It does not insist that everything be placed on a single timeline. It only insists that causes never come after their effects within regions where influence can flow. The speed of light is what draws this boundary. It decides which events belong to each other's stories and which remain separate. In doing so, it quietly protects consistency. No event can reach outside its allowed region to rewrite the past or rearrange consequences. This is why causality has a shape. It is not an abstract rule floating above reality. It is a geometric feature of space-time itself. Just as mountains guide rivers without effort, the structure of space-time guides cause and effect without enforcement. Seen this way, the speed of light is not about speed at all. It is about reach. It tells us how far an event's influence can extend as time moves forward. It sets the horizon of responsibility for every action in the universe. This perspective also helps dissolve a common confusion. When we hear that nothing can travel faster than light, it can sound like an arbitrary restriction. But what is really being said is much softer. Nothing can influence an event that lies outside its causal reach. The universe is not forbidding motion, it is maintaining coherence. There is something deeply reassuring in this. It means reality is not fragile. It does not require constant correction to prevent paradox. Its structure already does the work. Causes are naturally fenced into regions where their effects make sense. This structure also explains why the speed of light remains the same for all observers. If different observers disagreed on how influence spreads, then causality itself would fracture. One observer might see an effect before a cause, while another sees the opposite. The universe avoids this by making the boundary universal. Everyone shares the same causal structure, even if they disagree on distances and durations. As we rest with this idea, it becomes clear that the speed of light is the quiet architect of order. It is not flashy. It does not announce itself, but it shapes everything that can happen and everything that cannot. This understanding prepares us for the next step in the story. If causality has a shape, then anything that tries to outrun light is not merely moving fast. It is attempting to step outside that shape, and when that happens, time itself begins to fold in unsettling ways. The universe does not respond with alarms or prohibitions, it responds with impossibility. Certain paths simply do not fit. Certain stories cannot be told. And in exploring why that is, we begin to see why faster-than-light motion is not just difficult, but deeply incompatible with how reality keeps itself coherent. Once we begin to see causality as something with a shape, the idea of moving faster than light takes on a very different tone. It no longer sounds like a challenge of engineering or ambition. It begins to sound like a grammatical error in the language of reality. To understand why, we return to the idea of events rather than objects. Imagine a simple story. You send a signal. Later, it is received. The order feels obvious. First the sending, then the receiving. This sequence is so deeply embedded in experience that it feels almost invisible. But that invisibility depends on something very specific. The signal must travel within the universe's allowed causal structure. When influence travels at or below the speed of light, the order of events remains consistent for everyone who can be affected. Observers may disagree on details of timing, but they will never disagree on which event caused which. The cause always comes first. The effect always follows. Now imagine gently and carefully that a signal could travel faster than light. At first, it sounds harmless. The signal leaves sooner and arrives sooner. Nothing dramatic. But the geometry of spacetime has other plans. When motion exceeds light's pace, the shape of causality bends in an unexpected way. Events that were once safely ordered can slip past one another. For some observers, the signal would arrive before it was sent. This is not a metaphor. It is not a trick of language. It is a direct consequence of how space and time rearrange themselves when motion exceeds the speed that defines causal reach. Faster than light travel does not simply shorten travel time. It changes the relationship between time and order. To see why, imagine reading a book where the pages occasionally rearrange themselves depending on how fast you turn them. From one angle, page 10 follows page 9. From another, page 10 appears before page 9 has even been written. The story no longer makes sense, not because the words are wrong, but because order itself has become unreliable. This is what faster-than-light influence does to reality. It allows effects to appear in frames of reference, where the cause has not yet occurred. And once that door is open, even slightly, the idea of causality begins to unravel. From there, paradoxes emerge quietly but inevitably. A message arrives warning you not to send the message. A signal prevents its own creation. An effect erases its cause. These scenarios are often presented as dramatic puzzles, but they are better understood as symptoms. They are what happens when the universe's causal grammar is violated. Importantly, physics does not object to faster-than-light motion because it dislikes paradoxes. It objects because paradoxes signal inconsistency. A universe that allows causes to follow effects cannot maintain a coherent history. Events lose their ability to be stitched into narratives. Memory, prediction, and explanation all begin to fail. This is why it is helpful to think of light speed not as a limit on motion, but as a protector of order. The universe is not saying, you may not go faster. It is saying, if you do, the idea of before and after no longer works. There is a quiet elegance to this protection. The universe does not enforce causality through rules or policing. It enforces it through structure. Faster-than-light paths simply do not fit into space-time without breaking the relationships that give events meaning. A useful way to picture this is to imagine trying to read tomorrow's newspaper today. You might hold the paper in your hands, but the events described have not yet happened. The information has nowhere to come from. The act itself becomes meaningless. Similarly, a signal that arrives before it is sent is not merely early. It is undefined. This also explains why many apparent loopholes in faster-than-light discussions ultimately fail. They rely on clever arrangements that seem to avoid paradox at first glance. But when examined across all observers, the contradictions resurface. The universe does not allow special cases where order can be broken locally without consequences elsewhere. What is striking is how gently this conclusion arises. No exotic assumptions are required. No dramatic prohibitions are declared. The simple combination of relativity and the observed behaviour of light is enough. Faster-than-light influence naturally leads to backward time order for someone somewhere, and that is enough for the universe to quietly refuse it. This refusal is not dramatic. It does not come with alarms or cosmic barriers. It comes in the form of impossibility. certain questions stop having answers. Certain scenarios stop being definable. The universe does not say no loudly. It simply stops responding. There is a calm clarity in this. It suggests that reality is less about enforcing limits and more about preserving coherence. The speed of light protects the idea that causes give rise to effects, that stories unfold rather than tangle, and that time remains something we can live inside. When people imagine breaking the light speed limit, they often imagine freedom, unlimited travel, instant communication. But from the universe's perspective, such freedom would come at the cost of intelligibility. A reality where effects can precede causes is not more powerful. It is less meaningful. This is why physics consistently returns to the same conclusion, even across different theories and frameworks. Light speed is not negotiable, not because of conservatism, but because it underwrites the very possibility of sequence. Without it, the notion of happening itself dissolves. As we sit with this realization, the story naturally softens. The universe is not fragile, but it is particular. It allows many strange and beautiful things, but it does not allow contradictions to take root. Faster-than-light influence is not forbidden by decree. It is excluded by structure, and this leads us gently to a deeper reflection. If light speed is not a wall, but a boundary of meaning, then perhaps asking what lies beyond it is like asking what comes before. The question itself begins to fade, and in that fading, the universe remains whole. After walking through causality, paradox, and the fragile order of events, the idea of the speed of light begins to feel different. It no longer resembles a barrier you might one day break through with better engines or clever shortcuts. It begins to resemble something subtler, a boundary not in space but in sense. When we imagine limits, we often picture walls, solid obstacles that stand in the way of progress, something you can press against, lean on, or eventually break through. But the universe does not treat the speed of light like a wall, it treats it like the edge of a map. Beyond certain boundaries, questions do not become difficult, they become undefined. A helpful comparison comes from geography. If you travel far enough north, you eventually reach the North Pole. Once there, asking what lies further north stops making sense. There is no hidden land beyond, not because it is forbidden, but because the concept itself no longer applies. Direction loses meaning at that point. The speed of light works in much the same way. As long as motion remains within the universe's causal structure, questions about before and after, here and there, cause and effect all remain meaningful. They may be complex, but they are well posed. Once motion tries to step beyond that structure, the language we're using quietly breaks down. What would it mean to arrive before leaving? What would it mean for an effect to create its own cause? What would it mean for information to exist without a history? These are not puzzles waiting for clever answers. They are signals that we're asking the wrong kind of question. This is why the universe does not respond to faster-than-light scenarios with dramatic contradictions. It responds with silence. The equations stop describing anything physical. The stories stop being tellable. The universe does not object. It simply withholds meaning. Seen this way, the speed of light is not something reality enforces from the outside. It is something reality is. It defines the framework within which events can be ordered, stories can unfold, and explanations can exist. This perspective helps dissolve a lingering discomfort. Many people feel uneasy when they hear that something is fundamentally impossible. It can sound limiting, as if nature is holding back possibilities. But here, the impossibility is not arbitrary. It is structural. It is what allows everything else to work. A universe without such a boundary would not be more free. It would be less coherent. Without a shared limit on influence, there would be no stable notion of sequence. Memory would lose its anchor, prediction would lose its footing, even identity would become uncertain, as events could no longer be reliably connected. The speed of light quietly prevents all of this, not by force but by definition. It tells us which questions are meaningful and which quietly dissolve before answers are needed. There is a calm elegance in this restraint. The universe does not try to explain everything. It provides a framework within which explanation is possible. Beyond that framework, it offers no commentary, because commentary itself would have no place to stand. This is also why phrases like "beyond the speed of light" can be misleading. They suggest a region or domain waiting to be explored. But there is no beyond in the usual sense. There is only the edge of applicability for certain concepts. Just as there is no time before time begins in a story, there is no causal order beyond the boundary light defines. This does not mean the universe is small-minded or closed. On the contrary, it means the universe is carefully structured. It allows enormous richness, complexity, and variation, but it anchors all of it to a consistent core. In this moment of the story, it is helpful to pause, not to push forward, but to rest, to notice how much has already been revealed simply by respecting one constant. Light speed has led us from failed experiments through flexible time and space into the geometry of causality itself. Now it invites us to stop asking how to break it and start asking why it exists at all. This pause is not emptiness, it is preparation. Because there is another layer to the story, one that does not describe limits as prohibitions but as outcomes. One that shows how the universe naturally avoids forbidden paths without policing them. A layer where reality explores possibilities and quietly cancels the ones that do not fit. To reach that layer, we must gently shift our attention away from classical motion and into the strange whispering realm of quantum behavior. A place where the universe does not choose a single path, but considers many, and where impossibility reveals itself not through rules, but through disappearance. For now, it is enough to sit with the idea that the speed of light is not a wall you crash into, but a boundary that keeps stories meaningful. It is the line that separates questions that can be asked from questions that dissolve upon inspection. And in that quiet distinction, the universe reveals something generous. It does not promise answers to everything. It promises coherence, where answers exist at all. And that promise is what allows reality to hold together, moment by moment, without rushing, without contradiction, and without needing to explain itself further. After the philosophical stillness of the previous pause, the story does not restart with a bang. It drifts. It slips into a quieter layer of reality, one where the universe does not march along a single, well-defined route, but wanders gently through possibilities before settling on what remains. This is the quantum view, and it asks us to soften our expectations once again. In everyday life, when something moves from one place to another, we imagine a path, a single line connecting here to there. We picture a ball arcing through the air or a person walking down a hallway. One motion, one route, one history. But at the smallest scales, the universe behaves differently. Richard Feynman offered a way of thinking about this that is both strange and strangely calming. Instead of assuming that a particle chooses one path, he suggested that it explores all possible paths, not just the sensible ones, not just the efficient ones, every imaginable route, including those that loop, wander, hesitate, or seem completely absurd. This is not because the particle is indecisive. It is because reality itself does not commit early. In this view, a particle does not travel like a traveller following a map. It behaves more like a rumour spreading through a crowd, whispering along countless routes at once. Each possible path carries a whisper. Some whispers reinforce one another, others clash and fade into silence. What we observe is not a single choice, but the surviving agreement among all these possibilities. This idea can feel unsettling at first. It seems to suggest chaos or lack of control. But the opposite is true. The universe is not careless in this process. It is precise, even elegant. The exploration of many paths is not random wandering. It is a structured way of ensuring consistency. To picture this gently, imagine standing in a vast cathedral filled with echoes. You speak a word. Your voice reflects off walls, columns and arches. Some echoes return in harmony, strengthening the sound. Others arrive out of step and cancel each other out. What remains is not the loudest echo, but the one that fits the space. Quantum reality behaves in much the same way. Every possible path contributes something, but only those that align survive. The rest erase themselves through interference, not through force, but through mismatch. This is why outcomes in quantum physics feel probabilistic. It is not that the universe rolls dice in ignorance. It is that many possibilities compete, and only some remain coherent when combined. Reality emerges from consensus, not command. What matters for our larger story is that this process naturally respects the boundaries we've already encountered. Paths that would violate causality, that would imply faster than light, influence or backward time order, do not survive this process. They interfere destructively. Their whispers cancel out. No cosmic referee is required. No rulebook is enforced. The universe simply finds that such paths do not fit with the overall structure. They do not harmonize with the geometry of spacetime, and so they fade. This is a powerful idea because it reframes limitation as outcome. Faster-than-light paths are not banned. They are explored and then erased. They are tried and found incompatible. The universe does not forbid them, it forgets them. This forgetting is quiet and complete. There is no trace left behind. What remains are the paths that preserve causality, order, and coherence. From our perspective, it appears as though the universe always respected the speed of light. From within the quantum process, it is more accurate to say that the universe tested alternatives and found them unsustainable. This view also helps reconcile quantum strangeness with the calm predictability of the larger world. At small scales, possibility flourishes. At large scales, agreement dominates. The countless whispers average out, leaving stable patterns we can rely on. Chairs remain solid, clocks tick steadily, stories unfold in order. Feynman's perspective does not replace the earlier ideas of relativity. It deepens them. Relativity tells us what is allowed. Quantum mechanics shows us how the universe naturally arrives there without instruction. One describes structure. The other describes process. There is something profoundly comforting in this partnership. The universe does not rush to conclusions. It explores, it listens to itself, and then, quietly, it settles. In this light, the speed of light is not an imposed speed limit. It is the pace at which coherence survives. Paths that demand faster influence simply cannot stay in agreement with the rest. They fall out of step. They cancel. This cancellation is not failure, it is refinement. As we sit with this idea, the earlier questions about breaking limits begin to soften. The universe is not a machine with switches that can be flipped. It is a conversation among possibilities. Some voices harmonize, others disappear. The quantum view does not make reality less real. It makes it more patient. It shows us that consistency is not enforced from above, but negotiated from within. And this gently prepares us for the next step, If forbidden paths erase themselves, then faster-than-light motion is not dramatic rebellion. It is simply noise that cannot survive the conversation. To understand why this noise vanishes so reliably, we must look more closely at how interference works, and why some possibilities never leave a trace. That is where we drift next, into the quiet mechanics of cancellation, where impossibility does not shout, but fades like footsteps in shifting sand. Having seen that the universe explores many possibilities at once, we can now linger with a gentler question. If all paths are considered, why do some of them never show up? Why does reality feel so disciplined, so consistent when the underlying process seems so generous? The answer lies not in choice, but in cancellation. When the universe explores possibilities, it does not weigh them equally in a simple way. Each possible path carries a kind of rhythm. Some rhythms align, others clash. When many incompatible rhythms overlap, they do not add up to chaos. They erase one another. What remains is not the loudest possibility, but the most harmonious one. To understand this without equations, imagine walking across a beach at low tide. Each step leaves a footprint. But if the sand is loose and the wind is strong, those footprints blur almost immediately. Steps taken in conflicting directions smear the surface until no single path remains visible. Only when many steps reinforce the same direction does a trail persist. Quantum reality behaves in a similar way. Paths that agree reinforce one another. Paths that disagree wash out. The universe does not need to prohibit the erased paths. It simply cannot remember them. This is what physicists mean when they speak of destructive interference, but the term itself is less important than the image. Possibilities that are out of step with one another cancel. They leave no mark. They do not build history. Now consider what happens to paths that would involve faster-than-light influence. Such paths carry rhythms that clash violently with the rest of space-time. They imply effects without causes, arrivals without departures, stories without beginnings. When these paths are placed alongside all others, they fail to align. Their contributions oscillate wildly, never settling into agreement, and so they vanish. This vanishing is not dramatic, it is quiet and thorough. From the outside, it looks as if the universe never allowed these paths at all. From the inside, they were considered and dismissed by incompatibility. This distinction matters. It shows us that physical laws are not arbitrary fences. They are filters. They allow coherence to accumulate and incoherence to dissolve. Faster-than-light paths do not survive not because they are dangerous, but because they are noisy. Noise is a useful metaphor here. In a room full of conversations, a clear voice can be heard because it stays consistent over time. Random shouting, no matter how loud, becomes unintelligible. In quantum reality, faster-than-light possibilities shout in too many contradictory ways at once. They do not form a sentence. They do not tell a story. This is why we never observe such paths directly. There is nothing there to observe. No stable pattern emerges. No record is left behind. Importantly, this also explains why certain quantum diagrams can look misleading when taken too literally. In calculations, physicists sometimes draw paths that appear to bend backward in time or exceed light's pace. These drawings are bookkeeping tools, not photographs of reality. They represent intermediate possibilities that are added together and then erased. The danger arises only when we forget this context and imagine that every drawn path corresponds to a real event. But quantum mechanics is not a catalogue of happenings. It is a method for determining what survives. What survives are the possibilities that agree with the universe's deeper structure. Those that respect causality, that fit within light's geometry, that allow events to be ordered into histories. Everything else dissolves before it can matter. There is something quietly beautiful about this process. The universe does not need to enforce its rules with force. It does not need to monitor every possibility. It allows exploration, confident that inconsistency will take care of itself. This confidence gives rise to stability. The world feels solid not because it is rigid, but because it has been refined. Countless incompatible possibilities are constantly tried and erased, leaving behind a calm surface we can live on. In this sense, faster-than-light motion is not a hidden rebellion waiting to be discovered. It is a path that cannot keep its footing. Like footsteps in shifting sand, it disappears as soon as it is made. This perspective also helps us understand why reality feels classical at human scales. The more possibilities are involved, the more opportunities there are for cancellation. The universe averages itself. What remains is the most stable, least contradictory pattern. At small scales where fewer paths compete, strangeness survives. At large scales, agreement dominates. Faster-than-light influence never survives at any scale, because it never aligns with itself long enough to leave a trace. As we sit with this idea, it becomes clear that impossibility in physics is not always about prohibition. Sometimes it is about absence. Certain things do not happen, not because they are blocked, but because they cannot cohere. The speed of light, seen through this lens, is not an externally imposed rule. It is the pace at which coherence can persist. Paths that demand more simply cannot stay synchronized with the rest of reality. This realization carries a gentle reassurance. The universe is not brittle. It does not need to be protected from contradiction. It is self-correcting. It explores freely and settles naturally. With this understanding, we're ready to address one final source of confusion. If impossible paths are explored and erased, why do some calculations seem to suggest violations? Why do diagrams sometimes hint at particles popping in and out of existence, or slipping briefly beyond limits? To answer that calmly, we turn next to the difference between mathematical tools and physical events, and to the quiet role of virtual particles in helping us calculate without misleading us about reality. By now, it should feel clear that the universe has a remarkably calm way of maintaining order. It explores possibilities, allows them to overlap, and quietly lets incompatible ones fade away. And yet, despite this clarity, there is a persistent source of confusion that returns again and again whenever quantum physics is discussed. It usually begins with a picture. In textbooks and popular explanations, quantum processes are often illustrated with diagrams showing particles popping into existence, darting backward in time, or briefly moving faster than light before disappearing again. These images are vivid, memorable, and deeply misleading if taken too literally. The misunderstanding does not come from bad intentions. It comes from mistaking a tool for a photograph. The diagrams used in quantum physics are not drawings of what actually happens in space and time. They are accounting devices, visual shorthand, ways of organizing complex calculations so that physicists can keep track of contributions without writing pages of symbols. They help us compute outcomes, not witness events. Virtual particles live entirely inside these calculations. They are not particles in the everyday sense. They cannot be detected directly. They do not travel from one place to another carrying information. They do not have a history that can be told as a story. They are intermediate terms in a mathematical conversation the universe uses to decide what survives. A helpful way to think about virtual particles is to imagine rough drafts of a sentence. When you write, you might try several phrasings in your head before settling on one that feels right. Those discarded phrases were never spoken. They left no trace. But they helped shape the final sentence. Virtual particles play a similar role. They appear in the process of calculation and then vanish, leaving behind only the final, observable outcome. Treating them as physical objects is like treating your unspoken thoughts as recorded conversations. This distinction matters deeply when discussing limits like the speed of light. Some diagrams include lines that seem to violate those limits, but these lines do not represent things moving through space-time. They represent terms in an equation, contributions that will later cancel or combine. When all contributions are added together, the final result always respects causality. Information never travels faster than light. Effects never precede causes. The universe keeps its promises. The confusion arises when we look at intermediate steps and assume they are independently real. But quantum mechanics does not work that way. Reality is not built from individual steps. It is built from the final agreement. This is why physicists are careful about what they call real. Observable particles leave tracks. They carry energy and momentum. They can be detected and recorded. Virtual particles do none of these things. They are useful fictions, not hidden actors. It is tempting to imagine that these fictions point to secret loopholes, that somewhere beneath the surface, reality is quietly cheating its own rules. But the deeper truth is simpler and calmer. The rules are respected not only in outcomes, but in the structure of the process itself. Even in the quantum realm, information behaves conservatively. It does not leak into the past. It does not outrun light. The universe allows complex internal bookkeeping, but it never allows those internal steps to become observable violations. This distinction also explains why claims of faster-than-light communication based on quantum effects always fall apart upon careful examination. They rely on confusing correlation with influence. Entangled systems can show coordinated outcomes, but no usable signal is transmitted faster than light. No message is sent. No cause leaps ahead of its effect. Correlation does not imply communication. The universe is perfectly comfortable allowing strange relationships, as long as they do not carry information in a way that breaks order. Once again, coherence is protected not by force, but by structure. There is a kind of quiet honesty in this. Quantum mechanics does not hide loopholes behind complexity. It exposes its own bookkeeping clearly, as long as we remember what the symbols mean and what they do not. When we forget that, confusion follows. Diagrams turn into myths, metaphors harden into claims, and limits that are actually foundational begin to look negotiable. But when we slow down and listen carefully, the story becomes consistent again. Virtual particles are not travellers. They are terms. Faster-than-light lines are not paths. They're contributions that cancel. Nothing physical ever escapes the geometry of causality. This understanding allows us to rest more comfortably with the quantum world. We do not need to imagine it as a place of chaos or hidden rebellion. It is subtle, yes, counterintuitive, often, but it is also deeply disciplined. The universe does not say one thing in its calculations and another in its behaviour. The same structure that shapes space and time also shapes quantum processes. The same limit that protects causality also guides interference and cancellation. As we let this sink in, a reassuring pattern emerges. Every time it looks like reality might be breaking its own rules, a deeper look reveals that the rules were never broken at all. They were simply misunderstood. This is not a failure of imagination. It is a reminder that imagination must be paired with patience. Quantum physics asks us to think differently, but not carelessly. It invites us to hold multiple possibilities lightly, without assuming they all become real. With this clarity, one of the last lingering worries fades. The speed of light is not under threat from quantum weirdness. It is quietly upheld by it. Even in the most abstract calculations, causality remains intact. And now, with the classical and quantum pictures gently aligned, we are ready to widen our view again, to see how this limit shapes not just particles and signals, but entire regions of the universe, horizons, histories, and the boundaries of what can ever be known. That is where our attention drifts next. When we hear the word horizon, we often think of distance, a line where the sky meets the land, a place we can see but not reach. In physics, horizons carry a similar feeling, but their meaning is deeper. They are not about how far you can travel. They're about how far influence can extend. At the heart of every horizon lies the same quiet constant, the speed of light. A horizon forms whenever the structure of space-time arranges itself so that light, moving at its characteristic pace, can no longer carry information from one region to another. Nothing dramatic needs to happen. No barrier needs to appear. The boundary emerges naturally from geometry. Black holes are the most famous example of this idea. A black hole is often imagined as a cosmic vacuum cleaner, swallowing everything nearby. But this image misses the subtlety. A black hole is not defined by what it pulls in, but by what it prevents from sending information out. The key feature is not the center, but the boundary surrounding it, the event horizon. The event horizon is the point beyond which light can no longer escape. Once something crosses this boundary, its future paths all point inward, not because it is forced, but because space-time itself tilts in that direction. Every possible future lies deeper inside. It is tempting to imagine the event horizon as a physical surface, like the edge of a cliff. But nothing special happens at that boundary locally. An object crossing it does not feel a sudden jolt or hit a wall. From its own perspective, the journey continues smoothly. The drama exists only in relationships. For an observer far away, light emitted closer and closer to the horizon takes longer and longer to arrive. Signals stretch, clocks appear to slow. Eventually the light never arrives at all. The object seems frozen at the edge, fading but never quite disappearing. Both perspectives are valid. Neither contradicts the other. They simply reflect how time and causality organize themselves differently depending on where you stand. This is where the speed of light quietly asserts its deeper role. The horizon is not a place where things stop moving. It is a place where information stops being shared. The universe draws a line and says gently, "Beyond this, causes here can no longer influence effects there." Seen this way, black holes are not cosmic failures. They are extreme expressions of the same causal structure that governs everyday life. The same limit that prevents faster-than-light signals also defines the boundaries of these mysterious regions. What makes this especially interesting is that horizons are not unique to black holes. The expanding universe itself creates horizons. There are regions so distant that light emitted today will never reach us, no matter how long we wait. Not because space is blocking it, but because space itself is stretching. Once again, the speed of light shapes what can be known. These cosmic horizons remind us that knowledge is not limited by curiosity or intelligence alone. It is limited by causality. There are events in the universe that are real, meaningful, and complete, yet forever disconnected from us. Not hidden, not forbidden, simply unreachable. There is something quietly humbling in this realization. The universe does not promise that everything can be observed. It promises that what can be observed will be consistent. The event horizon of a black hole also teaches us something subtle about time. To escape from inside a horizon would require moving in a direction that no longer exists in the future. It would mean reversing the natural flow of time itself. This is why escape is impossible, not because of speed, but because of orientation. The future inside a black hole points inward. This idea can sound abstract, but it carries a calm clarity. Limits are not enforced by energy or strength, they're enforced by structure. To cross certain boundaries would require becoming something different, something no longer bound to time in the same way. And this returns us to a familiar theme. The speed of light is not a wall, it is a guide. It shapes the map of influence, the layout of what can affect what, and the edges of all possible stories. Black holes are often described as destructive, but in this light, they are preservers. They preserve causality by sealing off regions where influence would otherwise tangle. They allow the rest of the universe to remain orderly by isolating what cannot be shared. This does not make black holes gentle or safe, but it makes them understandable. They are not places where rules vanish. They are places where the rules reveal their full strength. As we reflect on horizons, it becomes clear that limits are not merely constraints. They are features that give shape. Without horizons, there would be no clear separation between cause and effect across vast scales. The universe would blur into a single, incoherent whole. Instead, it is articulated, divided into regions with meaningful relationships, connected where connection is possible, separated where it is not. This articulation allows history to exist. It allows events to have consequences without interfering everywhere at once. It allows complexity to grow without collapsing into contradiction. And this sets the stage for our next reflection. If the speed of light shapes horizons and limits knowledge, it also shapes time's direction itself. It influences why the universe has a past we can remember and a future we can approach. To understand that, we must turn toward the arrow of time and toward the quiet role that limits play in allowing stories to move forward rather than unravel. At this stage of the journey, the speed of light no longer feels like a detail of physics. It feels like a rhythm, a pacing that reality follows so gently that we rarely notice it. Yet this rhythm does more than limit motion or define horizons. It shapes history itself. To understand this, we turn to a familiar but often misunderstood idea, the arrow of time. Time, as we experience it, has a direction. We remember the past, not the future. Causes lead to effects. Stories unfold rather than rewind. This directionality is so natural that it feels inevitable. And yet, at the deepest levels of physical law, many processes are symmetrical. The equations often work just as well forward as backward. So where does the arrow come from? The answer is not found in time alone. It is found in limits. Entropy is the word physicists use to describe the tendency of systems to spread out, to mix, to move from order toward disorder. But this description can feel cold and abstract. A gentler way to think about entropy is to think about possibilities. Ordered states are rare, disordered states are numerous. Over time, systems drift toward what is more likely simply because there are more ways to be there. Now here is the quiet connection. For entropy to increase in a meaningful way, influences must be local. Changes must propagate step by step, not everywhere at once. If every part of the universe could instantly affect every other part, the concept of gradual change would collapse. There would be no direction, only immediate equilibrium. The speed of light prevents this collapse. Because influence travels at a finite pace, the universe evolves in layers. Events affect nearby regions first, then gradually spread outward. This allows patterns to form, persist, and dissolve over time. It allows history to have chapters rather than being written all at once. Imagine trying to tell a story where every sentence instantly changes every other sentence. Meaning would evaporate. Narrative depends on sequence. Sequence depends on limits. The same is true of the universe. Light speed ensures that information moves in an orderly way. It creates delays, separations, and gradients. These are not flaws. They are the conditions under which complexity can grow. Stars can form, life can emerge, memories can be stored, causes can leave traces that effects can later read. Without a limit on influence, entropy would not have a direction we could recognize. Systems would jump directly to their most probable states. There would be no slow unfolding, no aging, no learning. The universe would be static in the most extreme sense. In this way, the speed of light acts as a quiet guardian of time's arrow. It does not create entropy, but it allows entropy to matter. It ensures that change is not instantaneous, that processes take time, that the past can differ from the future in meaningful ways. This also helps explain why memory exists at all. Memory requires separation. The event must happen. The record must form later. The two cannot coincide. Light speed ensures this separation. It guarantees that causes precede records, that experiences leave imprints that can be revisited. Even at the level of thought, this structure matters. Neurons fire, signals propagate, patterns settle. None of this would be possible if influence were instantaneous. Consciousness itself depends on delay, on sequencing, on the gentle unfolding of cause and effect. Seen this way, the speed of light is not an inconvenience, it is a gift. It slows the universe just enough for meaning to emerge. There is a quiet irony here. We often imagine that faster would be better. Faster travel, faster communication, faster change. But a universe that allowed everything to happen instantly would be unlivable. It would be too smooth, too averaged, too flat. Nothing could stand out. Nothing could endure. Limits create texture. The arrow of time is not carved into reality by force. It is woven from the interplay between probability and constraint. Entropy provides the tendency. Light speed provides the pacing. Together they give the universe direction it can inhabit. This perspective also softens the fear that limits somehow diminish reality. On the contrary, they enrich it. They allow stories to be told rather than collapsed. They allow causes to echo rather than vanish. They allow futures to be approached rather than predetermined. As we rest with this idea, it becomes clear that the speed of light is not merely about how fast things move. It is about how slowly the universe allows itself to change. Slowly enough for structure to form, slowly enough for history to be written. And this brings us gently to the final reflection. If light speed shapes motion, causality, horizons, and the arrow of time, then it is doing something even deeper. It is setting the rate at which reality itself updates, the pace at which the universe can respond to itself. That final idea is not about physics alone. It is about existence, and it is where our journey naturally comes to rest. As we arrive at the end of this long, gentle journey, the speed of light no longer feels like a technical detail hidden inside equations. It feels like a heartbeat, a steady rhythm that reality follows, moment by moment, whether anyone is watching or not. Up to now, we have seen how this rhythm shapes motion, causality, horizons, and history. But there is one more way to understand it, one that gathers all the earlier ideas into a single quiet image. The speed of light is the update rate of reality itself. In any system that changes, there is a pace at which information can be refreshed. In a conversation, it is how quickly words can be spoken and heard. In a story, it is how fast one event can follow another without confusion. In a living organism, it is how quickly signals can travel before coherence is lost. Reality is no different. The universe is not static. It is constantly responding to itself. Fields adjust, particles interact. Events leave traces that future events must respect. For this to remain coherent, updates cannot happen everywhere at once. They must propagate. They must take time. The speed of light sets that pace. When something happens, its consequences spread outward at a finite rate. The rest of the universe is not instantly informed. This delay is not a flaw. It is what allows different regions to have their own local stories, their own moments of becoming, without collapsing into a single overwhelming instant. If reality updated infinitely fast, everything would happen at once. There would be no sequence, no anticipation, no memory. The universe would be frozen not because nothing happened, but because everything happened immediately and indistinguishably. Instead, the universe updates gently. Each moment builds on the last, informed by signals that arrive when they are able, not before. This gives existence a texture, a sense of unfolding, a chance for complexity to arise and persist. Seen this way, the speed of light is not a restriction on ambition. It is a guarantee of stability. It ensures that reality does not tear itself apart by responding too quickly to every fluctuation. It allows patterns to settle before being disrupted. It gives time for coherence to form. This is why the universe feels solid enough to live in. Stars burn steadily rather than flickering unpredictably. Planets maintain orbits rather than constantly rearranging. Living systems can regulate themselves rather than being overwhelmed by instantaneous feedback. Even thoughts have time to form before being replaced. All of this depends on a finite update rate. There is a quiet wisdom in this restraint. The universe does not try to be maximally responsive. It tries to be sustainable. It values continuity over immediacy. It allows causes to breathe before effects arrive. This also reshapes how we think about limits. A limit that stabilizes is not an obstacle. It is a foundation. Without it, the structure above cannot stand. The speed of light holds reality together not by force, but by pacing. It ensures that no part of the universe outruns the rest so completely that meaning is lost. Everything stays in conversation, even if that conversation takes time. From this perspective, faster-than-light travel no longer appears as a forbidden dream. It appears as a misunderstanding of what makes existence workable. A universe that could rush faster than light would not be more free. It would be less intelligible, less stable, less alive. The universe we inhabit has chosen a different balance. It allows immense speed, but not infinite speed. It allows vast distances, but not instant connection. It allows change, but not chaos. And in that balance, something remarkable happens. Reality becomes inhabitable. We can make plans because the future is not instantly rewritten. We can remember because the past does not dissolve. We can learn because causes and effects remain aligned long enough to be understood. None of this would be possible without a shared pace. In this sense, the speed of light is not about light at all. It is about trust. Trust that the universe will not rearrange itself faster than meaning can keep up. Trust that events will have time to become what they are before being replaced. As we let this idea settle, it softens the entire story we've been telling. The failed experiments, the flexible time, the quantum whispers, the vanishing paths, the horizons, the arrow of time. All of them point toward the same quiet conclusion. Reality holds together because it cannot rush. There is a deep comfort in that. In a world that often feels hurried, unstable, and overwhelming, the universe itself sets an example of patience. It changes, yes, but at a pace that allows coherence to survive. As you rest here, perhaps letting your thoughts slow along with the story, it is worth noticing that this same rhythm is present in you. in your breathing, in your heartbeat, in the way thoughts arise and fade. None of it is instantaneous. All of it unfolds. The speed of light is woven into this unfolding, not as a number to memorize, but as a principle to feel. It is the quiet agreement that makes existence possible. And so, we come to the end of tonight's exploration. Whether you're still listening closely or already drifting towards sleep, the universe continues its steady update, moment by moment, holding itself together without haste. Nothing needs to outrun anything else. Nothing needs to arrive before it is ready. Reality moves at the pace it can sustain, and that, perhaps, is why it lasts.